Today we are going to look at Unit 1, question 10.3. Define the sequence W so that W of n is the number of white squares in step n, and define the sequence B so that B of n is the number of black squares in step n. So first let's focus on the number of white squares. If I'm looking at this, I like to make a table. So if I am looking at my step number and the number of white squares. In step 1, I have 10 white squares. In step 2, I have 14 white squares. And in step 3, I have 18 white squares. Looking at this, I can see that the number of white squares is adding by 4 each time. I'm adding 4 squares to each new step that I see. Because I'm adding squares and I'm adding the same amount each time, I know that sequence W is arithmetic. That's what I know. If I'm looking at the number of black squares, let me make a little table with this information. At step and B of n. Step 1, I have 2 black squares. Step 2, I have 6. And step 3, I have 12. This one's a little bit harder. Am I adding the exact same number for this particular sequence? No, I'm not. Am I multiplying by the same number each time? I'm not doing that either. I know to get from 2 to 6, I would multiply by 3, but then to get from 6 to 12, I would multiply by 2, so not the same number. That means that sequence B is neither. It does not have a constant growth rate or a constant rate of change. Let's start writing our equations for these sequences. Now, we know how to write a recursive formula. We also know how to write a non-recursive formula. So let's first start with sequence W. Sequence W is adding by 4 each time, which means it's an arithmetic sequence. If we were to look at this on a graph, it's going to be represented by a linear graph. So to write my recursive formula, I know I have to start with my first step here. So I know step 1 has 10 white squares in it. To write my recursive formula, I would write W of n equals W of n minus 1, because remember, the recursive definition always depends on the term before it. So I would have W of n minus 1, and in this case, it's just plus 4, because that's what we're adding by each time. Now this recursive formula will work for values greater than or equal to 2. Now, to write the non-recursive formula, it's a little bit difficult. So we know that we are looking at a line because this is an arithmetic sequence. So if we're looking at a line, we actually need to have our step 0 term. So if I think about this, to go from step 1 to step 2, I know I have to add 4. I know to get from step 14 to 18, I have to add 4. So what if I was working backwards? If I was working backwards and I started at 10, I would have to subtract 4 to get a value of 6. So I know my step 0 term is actually a 6. I'll have 6 white squares there. That information is going to be very helpful when we're writing our equation. So when we have to write our non-recursive equation, we still start with W of n, because this will work for any n value. Our rate of change, our constant rate of change, was 4. So I know I will have 4n. And then my y-intercept, or my step 0 value, is a positive 6. And I know that this equation will work for any n value that's greater than or equal to 1. And I know that because that's what I'm starting with in my step 1. Now let's try to do the same thing for our black squares. For our black squares, we still have to find, there is a relationship, we still have to kind of find out what we're doing. So if I look at this, I know to get from 2 to 6, I'm adding 4. To get from 6 to 12, I'm adding 6. Now I can start to see a pattern that is emerging. It is not arithmetic because although we are not adding the exact same number each time. Let's see if there's a relationship between these numbers that we're adding and our step number. You should see that we are adding the step number times 2 each time. So to write my recursive formula here, I am going to first start with b of 1, which is 2. That's our first term in this sequence. Then I know we got b of n equals b of n minus 1. And we know that each time the number that we're adding is actually 2 times the step number. So we would write that as 2 times n. And this formula can be used for all n values greater than or equal to 2. Now, writing the non-recursive formula is a little bit more difficult. So let me erase what I have written up here so we can look at this as a shape. When I am looking at the dimensions of this shape, the black squares that are in the middle, it's actually representing a rectangle each time. What I mean by that is, in step 1, I have a 1 by 2 rectangle. In step 2, I have a 2 by 3 rectangle. In step 3, I have a 3 by 4 rectangle. So we have to figure out how to relate the numbers that we have to our step number. When you look at it, the way I'm highlighting it, I'm color coding it for you, we can see that for our first rectangle, the step number is the height of our rectangle, and the length of our rectangle is our step number plus 1. So for step 2, I have my step number here, and then I have my step number plus 1 up here. Lastly, I have, let me change colors. I have my step number of 3 here, and up top, I have my step number plus 1. So if I were to write this, I have my step number, and then I would have my step number plus 1. That's how I'm going to get each of my values in my number of black squares. If I were to look at this as a table real quickly, for my number of black squares, I have step 1, I have 2 black squares. Step 2, I had 6 black squares. And step 3, I have 12 black squares. So what I'm doing is just multiplying the height of the rectangle times the length of the rectangle. So just to clarify what I'm saying, if I look at my orange rectangle here, this value is 1 times 2. When I look at my second set of values, I have my second number is 2 times 3. And to get to this step, I'm looking at my values 3 times 4. So to write the equation that's non-recursive for this sequence, I would just do b of n is equal to n, which was my step number, times n plus 1. This will work for all values greater than or equal to 1. So we've now answered numbers 2 and number 3. To answer number 4, is the number of black squares ever larger than the number of white squares? Explain how you know. I think the easiest way to do this is to just make a table. We already know how to find our values. So let's try to make a table. I'm going to get rid of some of this stuff for us. Scooch that up. In order to do this, I'm going to erase some of this to give us some room. You should have this written down already. So when I look at this, I know I have my step number. I know I have the number of white squares. I know I have the number of black squares. Let's do a couple of these. Let's go up to step 6 and see if we can get information that we need. I know for step 1, we had 10 white squares. Step 2, we had 14 white squares. And step 3, we had 18 white squares. Now we're just going to extend the pattern. You can either extend the pattern using any rule that you came up with, or you can use either of the equations that we wrote. So I know I'm just adding 4 each time. So 18 plus 4 is 22. 22 plus 4 is 26. 26 plus 4 is 30. So now let's look at the black squares. Step 1, we had 2. Step 2, we had 6. Step 3, we had 12. Now remember, we wrote 2 different equations on how we can look at this problem. If we are looking at our recursive formula, we are taking our previous term and adding 2 times n. So for our next term here, we would do 12 plus 2 times 4. So 12 plus 8 gives us 20. So now we have 20 plus 2 times 5, which will give us 30. 30 plus 2 times 6, that gives us 42. So to answer this question, is the number of black squares ever larger than the number of white squares? Yes, it is. We showed that right here. So when our n value is greater than 4, the number of black squares will be higher.